The following program is brought to you by Caltech.
All right, welcome back. I'm very pleased to introduce Professor Nate Lewis, who is the George L. R. Gyros Professor of Chemistry and has been on the faculty of Caltech since 1988 and has served as a professor since 1991. Professor Lewis has a list of accomplishments that are too long to recount in full, so I'm going to omit almost all of them. I want to say that his research has been instrumental in allowing Caltech to be chosen as a lead for the newly created Joint Center for Artificial Photosynthesis to run the Department of Energy's Fuels from Sunlight Energy Innovation Hub. And we are very fortunate that Professor Lewis has offered to talk to us about some of his current research. Welcome.
Great. Thanks. Thanks. Well, actually, I'll tell you one of the two things that I actually am proud of in my CV. So I claim to be the only, faculty member that can make the following statement on the planet. With 98% fidelity, I have taught every undergraduate at my institution for the past 23 straight years. Because I teach, as everybody must know, Chem 1A. Everybody has to take Chem 1A. There is only one rec session of Chem 1A, and so if there is a way out of Caltech, it is through me, right? And I think, I first thought that Linus Pauling had done it for a lot longer, and I had heard rumors of 34 years. But then I traced it back. I had Judy Goodstein look it up, and actually Pauling, about 5 years ago, I had her look it up. I thought I had another decade to go to even get close to Hal Ripken Jr., Linus Pauling. But it turns out he only actually taught it for 13 years. He had Jörg Wasser and other people teach it, and the closest I've come is Tommy Apostle. Some of you probably like me. But even he never taught he taught Math 1 and Math 2, and not everybody took Math 1. Some people placed out. Some people went to .9. So I got a good 2 more decades to go to get to my 45th, but I'm going on my 24th starting a week and a half from now. So I'm the only way out of this place. I intend to keep it that way, right? Now, I did it in 1977. I had Chem 1A from Harry Gray. So I teach, of course, from Harry's book. It's just kind of keeping the ball rolling internally here. So I'm really proud of that one. The other one that hardly ever scientists get is in a completely random survey, as far as I can tell, if you look at that esteemed scientific periodical, the Rolling Stone magazine, you will find that in 2009 they named the 100 top agents of change in America, and I have absolutely no idea, but it was the only thing that's ever impressed my teenage son about my professional accomplishments. Was when his dad made the Rolling Stone, and when LeBron James was number 54, when Kobe Bryant wasn't even on the list of agents of change, when Bill Gates was 42, when Steve Chu was 24, when Al Gore was 18, and I was 17, he ripped it up saying it had to be a joke, right? Okay. But you can go check it out. Guaranteed. Okay. The reason I'm going to switch is because I had decided I was going to tell you all about my latest, greatest research in my lab, which I will do. But you probably have also, if you've been over to Chandler, to the cafeteria with its delicious food on the way to the F tonight, you will see a building that looks like a house of cards, Jorgensen, which, if you were like me, used to have the big flashing light that said batch in progress, that you would go to the desk when the IBM 3600 mainframe was there, and you would submit your job of Fortran cards, and back would come a pile of error messages this high. And then you would go through them all and submit a job, and if you were lucky, the program ran, and they put it on these big magnetic tapes. My PDP-11 here in noise, the lights really flashed when I did computation on it. My students don't believe such things. They think, but it was true. Well, Jorgensen, which was a computer science building for years and years, is now being changed to an energy building. And the 2 occupants of new Jorgensen to be building opened, we hope at the middle or end of April next year, will be the Resnick Institute for Sustainable Energy and will be the southern site of the Joint Center for Artificial Photosynthesis, JCAP. And so I think I should spend a lot of the time telling you about JCAP, about what is going on. It was in 2 months from Christmas 2 years ago, when it was announced on December 22nd until the end of February, turned into an 886-page proposal. The 3rd largest proposal ever written at Caltech. The first one was JPL. That's pretty hard to beat. The second one was for LIGO. We're actually a bigger project than LIGO now. I believe will be the biggest project on campus. And so I thought I'd tell you what that was all about and why we're all excited. And if you recognized the other thing we're all really proud of course, in the State of the Union last address, President Obama called out Caltech and said at the California Institute of Technology, they're taking sunlight and water and turning it into fuel for our cars, and them is us. All right, so that's what we're doing, and that's what that was all about. And so I thought I'd tell you what's going on and why we're doing that. If you want to find more details, then you can, of course, go to our website, none other than solarfuelshub.org. Now, you might ask how long we squatted on that name before the proposal was announced, as we were the winners, but we were going to sell it to the winners if we didn't end up that way. But it was actually positive thinking, so it was a good site to have. You can also get it at jcap.caltech.edu. You can watch out for it. Let me give you a little perspective on the big picture, which, by the way, I'm sure many of you are familiar with, but if you need the Nate Lewis big picture of energy on our planet, all you have to do is go to either my website or to a Watson lecture that I gave about 10 years ago on this topic. Doug Smith wrote it up in Engineering and Science, and we're all still very proud of how that has been effective at communicating this to scientists and the general public. The idea is pretty simple. Right now, if that happens in my class, you know what? I have a rule. If your cell phone rings in my class, I own it. And I prefer Verizon because I already have my own AT&T phone. So I'm a tough teacher, what am I going to do? All right. If you take global energy demand today, we use 15 trillion watts of energy per second. That's the burn rate of energy, 15 terawatts. So don't talk to me about a few light bulbs in Fresno or a few megawatts here and a few gigawatts there. A nuclear power plant's a gigawatt. You want to replace all the energy on our planet by 2050, like President Obama said we were going to replace 90% with clean energy by 2050? It takes a new Fukushima nuclear power plant every single day, starting today, to get from here to there by 2050. Because they're 1 gigawatt each electrical output, you got to make 15,000 of them, and there's only 14,000 days left between now and 2050. So that's the scale of energy. I am not against nuclear power. In fact, it's the only proven technology that we have that could scale to the levels needed to match global energy supply today. And even if you conserved energy like your lives depended on it, because they probably do, that all projections show energy demand will still probably double because it would triple. Otherwise, due to population growth and economic growth, yes, we can have global recessions and they slow everything down, but they don't stop it. And so if we're even very lucky and we actually didn't use any more energy in the next 10 years than we used in the last average year by year 10 years, something the world has never done in human history, you would still have to build 1 nuclear power plant every day to catch up by 2050 to where we are now. Okay? So this is scale. This is what separates microprocessors and information technology. Energy technology is not two guys in a garage turning into a Google in 3 years. You have to make a lot of stuff to make a lot of impact in energy. Well, if you can't get it all from fossil fuel, if you don't want to build a nuclear power plant every day, if you only build one a week, you leave 90% of the problem on the table. Well, actually, I believe in the Willie Sutton principle of energy engineering. All right, so what's the Willie Sutton principle of energy engineering? Willie Sutton was the bank robber that when they asked him, when they finally caught him, legend has it, Wikipedia, source of all knowledge, says no, but the legend has it, when they asked him, why do you rob banks, Mr. Sutton? He said, because that's where the money is. So more energy from the sun hits the Earth in 1 hour than all the energy consumed on our planet in an entire year. Nothing else comes remotely close. So the Willie Sutton principle of energy engineering says go to the sun because that's where the energy is. Rick Smalley, partner of mine, Nobel laureate, I was proud to kind of tour the country before we lost him tragically to leukemia about 5 years ago, testified in Congress that he thought that nuclear fusion was by far the solution to all of our energy problems, but that it was proven that it was not too safe to be too close to a nuclear fusion power plant, and 93 million miles away sounded just about right to him. All right. On the other hand, you see, Caltech, they get the joke. Most places I have to explain DD. Get it. It's a good crowd. But, you know, we're the land of O.J. Simpson and Johnny Cochran, and, you know, we know that if the glove doesn't fit, you have to acquit. The energy saying is, he that cannot store shall not have power after 4. The sun has this nasty little habit. Last time I looked, it goes out every single night. And so if you can't store it, no amount of photovoltaic cells is ever going to provide the sun into baseload power to get it wherever you want it, wherever you need it. No matter what we do, it's going to go out every night. And sometimes it's going to go out for 36 hours on a cloudy day, and sometimes for 72 hours. So you can say, how would you store it? Well, people pump water uphill. That's good for summer versus winter. But let's think about the volume you'd need just for a day and a night. You want to pump the amount of energy in 1 gallon of gasoline, you have to pump 55,000 gallons of water up the height of Hoover Dam. It's because the difference between a chemical bond energy and MGH is given by the laws of physics. There ain't enough water, there isn't enough reservoirs, there aren't enough dams, and there aren't enough pumps to even think about getting close to pumping water uphill every day and every night to do that energy scale job. You could compress air. People talk about compressed air energy storage, but it's the energy density problem that will cream that too. We know that. How far do you think you can go in your car by deflating your tires? Okay? Not very far. Okay? So you can talk about batteries. The energy density in the best battery is 200 watt hours in a kilogram. The energy density in gasoline is 13,000 watt hours in a kilogram. And you don't need to know anything more to know why it's always going to be a struggle to get range out of electric vehicles. It's a law of physics and chemistry that says that you have to carry your reactants and your products in a battery, and you get your other reactant, oxygen, for free from the air when you burn gasoline. You vent your CO2 and water as products. To give you a feeling, Tom Friedman, my friend, puts in his book even, if you read Hot, Flat, and Crowded, I highly recommend it, not only because he's my friend and been here twice, because I'm quoted about 50 times in the book. So you'll see that the good analogy is, how would you feel if every time you were on the freeway, every mile, everybody stopped, lowered their windows, and dumped out 1 pound of trash? Actually, that's exactly what we do. Every day, every mile we drive, we dump out on average 1 pound of CO2, and Hummers are 2. And when our former governor, we're proud to know, visits next week, I'm going to point out to him that his Hummer makes 2 pounds of trash out the tailpipe every mile he drives on the freeway. Of course, unless we make them hydrogen cleanly to change that. You know this is true about batteries because, after all, you can't even power that dinky dome light in your car overnight without draining the thing. Imagine how many batteries you'd need to power your whole house and your dishwasher and your plasma TV. It's not going to scale. So what can scale? The only storage other than the nucleus that the laws of physics say is energy dense enough to come close to what we now do in chemical bonds is chemical bonds. Chemical fuels power our planet for a good reason, because their energy density is 13,000 watt-hours in a kilogram, and hydrogen is 33,000 watt-hours in a kilogram, and nothing else even has the same zeros behind it. Okay? So if you want to scale energy storage, if you want to ever bring intermittent resources like sun or wind or any other intermittency into big time, you have to find a way to massively store them, and I think that means chemical fuels. So we want to take the biggest energy source and store it in the best way we can, chemical fuels. Well, nature kind of figured that out a long time ago, because that's in fact why we care about biofuels in plants. All the oxygen in our atmosphere came from photosynthesis. All the reduced carbon came from photosynthesis. That's the fuel that made fossil fuel that we now burn at a much faster rate than we were given it. But it's doing exactly that. It's a machine that takes the sun and stores the energy in chemical bonds. So why don't we just do a lot of plants? Well, you heard Frances Arnold. She's doing some wonderful things with making biofuels a reality. But if you're an engineer and I take a class and I come up with a problem that says create a machine and capture directly the sunlight and make fuel, and you come up with the plant, I'm going to give you an F. Because less than 1% of the total energy of the sunlight over a year, over a square acre, in the fastest growing plant, taking all the energy and all the chemical bonds of that plant, is actually retained in all the biomass of the fastest known growing plant on our planet. Less than 1%. That's the gross primary productivity of photosynthesis. Okay? So birds have feathers and they fly, but Paul MacCready would never build an airplane out of feathers. All right? We can do better as scientists and engineers, and we have to do better to minimize the land area because we don't want to trade food for fuel. We don't want to use potable water. We don't want to use arable land. And we don't want to use as much land as it takes when you have less than a 1% efficient solution to try to scale to our global energy needs. And because the only choices are build all those nukes or get it all from the sun or some other coefficient in between, then I think you can pretty easily see why the Department of Energy said, you know, we should be really trying hard to find a way to directly make fuel from the sun, but do it better than plants do, to have that as an option. Because actually I believe, just like my friend Stephen Chu, the Secretary of Energy, that science and technology has got us into this mess. And it's only through science and technology that we can get better choices to get us out of that mess. We're never going to legislate it. We're never going to incentivize it. There isn't enough money in all the governments in the world to incentivize all the needed clean energy technology at scale we need. The best way to make people sign treaties to bring on clean energy is to make it the cheapest energy, and then they won't need a treaty. They're going to do it. That's our job. Okay, so that's my introduction. That's why we're here. That's why we're doing what we're doing. Now, we can actually convert sunlight into chemical fuel right now. If you wanted to make hydrogen, you could take solar cells on the roof and wire them up to electrolysis units in the basement, the reverse process of fuel cells that Susina talked to you about. And we've done it in high school. You take the battery, the power supply, and you have two electrodes, you bubble out hydrogen, oxygen gas, and you hope it doesn't explode over the platinum and you run away. But you had to use platinum. The only stuff that's any good, actually platinum and even rarer metal, ruthenium dioxide, RuO2, is the anode. So this works fine on the space shuttle. JPL and NASA developed a series of fuel cells and reverse electrolysis-based fuel cells to both make and consume things for astronauts in space. But because they use rare and expensive metals, it's not scalable on Earth to the global energy demand that we would need. So we have to find a way to replace those metals, but we'd better do it in an integrated way because all that balance of systems and wiring is really expensive, and plants, last time I looked, don't have any wires. And that's a good thing. You know, people say, why don't you just run electricity? Because actually, electricity is an expensive way to distribute energy. And I can tell you why you must know that. Because when you go to the gas pump and you fill up at the gas station your car, if I asked you to guess, maybe this audience, but most audiences don't even know how many zeros, how many watts of power is the equivalent you are putting into your car through that gas pump when you fill it up. And anybody here know the answer to that? Even guess the order of magnitude in watts? 1,000? 50,000? 100,000? 1 megawatt. Oh, do I hear more? Okay, actually, we could have done this if I would have learned the kind of engineering rule. If you figured out how many horsepower a typical engine is, you would know that engines are roughly 50 or 100 kilowatt power plants. And you also know that you run your car for about 100 times longer than it takes you to fill it back up. And so that means you should multiply by 100, which you could also get by figuring out the energy in a gallon of gasoline and how many gallons you run per minute to fill up your car. And either way, of course, you get the same answer, 10 megawatts through a $5 piece of plastic pipe. Okay? Now try delivering a transmission line with stored electricity, 10 megawatts through a $5 piece of anything. It's $1 million a mile per megawatt to build the transmission line. Okay? So electricity is a high-value energy, and we pay a huge premium to move it from place A to place B when we flip the switch, and that's not stored. There is no way to store massive quantities of electricity except in the fossil fuels that we use to burn in those natural gas peakers when we need to unstore it and then turn on the lights. Okay? So now you have the setup. So we can do better than plants. Why can we do better? Because plants are green. They should be black to be optimum energy conversion machines. They were not optimized to be energy conversion machines in the same way that birds aren't optimized to fly fast, like airplanes, right? On top of that, a little-known secret. There are two photosystems in photosynthesis. We all know that. And there's a coupling between the two that's a molecular shuttle. That quinone that has to move physically between those two sites to carry the electrons in that Z scheme between photosystems is a physical motion of a molecule, and that acts as an ultimate time limit on the rate at which you can carry current between one system and the other. And that's such a stringent limit that actually the so-called D1 protein in all photosystems is unstable and is repaired every 30 minutes. So plants rebuild their photosystem critical components every 30 minutes. And in fact, it takes about 30% of the energy they would have produced just to parasitically be consumed to run the machine to keep it building and running all the time. At Caltech, we call that overhead. But it's a higher number than 30%, so we'll be, if we can get it down to the biological limit, we'll be doing well. All right. Nevertheless, it's a necessary but evil contribution to plants. In addition, in order to prevent that radical damage from going even more quickly, plants actually shut themselves down in productivity photosynthetically at 1/10 the light intensity of the sun. And that's a well-known phenomenon, again, related to this radical damage. So if you had a photocell, a photovoltaic, that shut down its current production at 1/10 the light intensity of sun, you would declare complete failure. But that's what photosynthesis does today, right? So we can do better because we know we can build photovoltaic cells that don't saturate. We know instead of 1% efficiency, they can be 10, 15, 20%. You can buy now 15% efficient solar panels. But that's not a solution for us because we want to make fuel and we have to integrate the fuel right up front production with the light absorption. Okay, so now we're into JCAP. So after 30 years, there is actually, I don't know if I even have it here. Yes, there is. Aha, good. This is JCAP. JCAP is a, I argue, bold, new way to do science. It is as much an experiment in the scientific enterprise as it is a challenge for us to do the science. That's actually why I'm so excited about it. The elements of JCAP are all captured in this one diagram, about which I will spend almost the rest of the time talking about, because I've decided this will be much more interesting than going into the details of what we do, but I'm happy to do that later. We are all at once taking teams of people, chemists, material science, physicists, applied physicists, theorists, we let them in the room too, engineers, mechanical engineers, chemical engineers, all at once, all in the same building, all devoted to the same one goal. Make something that can be scaled onto the scale of photosynthesis that outproduces those plants to make fuel from the sun by a factor of at least 10. We have to develop the nanoscale pieces that can do that, can absorb light and convert it into electrical charges. Those electrical charges have to make and break chemical bonds. And as many graduate students are very disappointed to find out, the sun, unfortunately, is not a laser. And that means that the photons aren't coherent. They come in one at a time, uncorrelated. And so those electrons are uncorrelated, but you need two to make and break a chemical bond. You can have at least two at once in the same place at the same time, and for that we need catalysts to do that. But those catalysts can't be platinum and RuO2 because there just isn't enough of it to scale to areas that we would need to actually make a difference on energy. So we have to find other systems. Now we know those other systems exist because nature found them. The hydrogenases that bugs use to make hydrogen have a cheap metal, iron, not platinum. They're not poisoned by carbon monoxide. They actually use it in the molecule to function. They use sulfur, poisons platinum, in the molecule to function. Doug Rees here has helped solve some of the crystal structures of the active sites of things in nitrogenases and hydrogenases. We now know their structures. We now can go make model compounds that hopefully will function like that, but put them in our artificial system instead of in the bugs that have all these other problems. We know that the source of oxygen on Earth is the oxygen evolving complex in photosystem 2, the manganese complex, not ruthenium, the cheap Earth abundant metal. We know these things exist. And we have to go, as chemists and material scientists, go make things that work like that. They won't look like that in the same way that birds don't look like airplanes. They're going to function like it because we know it's possible to fly because we've seen the evidence that it can be done. But if we get those pieces, if we get the world's best catalyst and we get the world's best light absorber, we already know if we take platinum and put it on silicon, the platinum poisons the silicon and the silicon poisons the platinum. And so it's not enough to have a team working on that and a team working on that, because if you don't put them together from the beginning, you end up with nothing. So we have, I'm proud to say, the Caltech Berkeley collaboration on the Mr. Potato Head team. Their job is to put the pieces together and make it look like the smiley face, not like the frowny face. All right? They have to take all the pieces from all the stovepipes and make sure that the integrated system actually works. They have to have a membrane to hold it together. Because if you don't have a membrane to hold it together, you'll make hydrogen and oxygen in the same place at the same time. And although we have colleagues at our sister institution, MIT, that say you don't need a membrane, you know, they still have a little bit to learn about the Hindenburg, I think. So we'll let them eventually figure it out. After you have the membrane to hold it together, you better learn how to scale it up. Because if there's a $122 million sunk into JCAP and I make something this big and I have to go to the president and say, here's what we spent our money on, you know, can't do that. We have to learn how to make big areas of this stuff, and it all has to work, and it has to be plumbed. We have to collect gases and products. We have to input reactants. We have to get the sun in there. We have to make sure that birds don't doo-doo on it in the wrong place, and we can clean it off, and it all has to be scaled up. So we have engineers and manufacturing people involved so that what we do at this scale is credible at this scale, and we're not waiting to solve these problems to do these things, so that we have prototypes that we're starting to build today that we know are going to fail. And I am so proud that we were the only team out of the 20 teams that when we went into our reverse site visit, when they asked us, are you sure you're not going to waste the taxpayers' money and that this is going to work? And I said, no, we're sure we're going to fail. I said, we're going to waste your money the first time. We're going to waste your money the second time. We are going to fail. But We know we're going to fail, and we're going to learn from our mistakes because we're willing to take risk and we're willing to learn. And the only way to get the fifth one that works is to make sure that we have enough courage to build the first four that don't. Because if we guaranteed it worked today, then that means we didn't have to learn anything, and you shouldn't be paying us a dime. It worked. Got the money. Okay. So why do we have this? Because the Secretary of Energy, Stephen Chu, a Nobel Prize winner, arguably the only Secretary of Energy that even knew what the words artificial photosynthesis would mean, said that this would be an important thing for the Department of Energy to work on, which was also validated by peer review based on the logic that I told you. Biggest energy source, best way to store it. There we go. Makes sense. Let's try to do that. And because these hubs, there are 3 of them, by the way. Hub directors talk to each other regularly. There's one in the next generation nuclear power plants, all done in computational modeling and simulation. Can you model and simulate a next safe generation of nuclear power plants? It's a great thing to be doing. There's another one on building efficiency. How can you retrofit buildings and make them efficient given that every building is different than every other one? That's by a former colleague of mine, Hank Foley. He's leading that out of Penn State. And then there was the one announced in Fuels from Sunlight that there was a national competition. There were 20 teams last March. There were 4 that were announced in the March Madness to go to the Final Four. Last March, a March ago. And then in June, we had a reverse site visit to Washington, D.C., where we sent a team of 8 people. And we ended up getting announced and selected shortly thereafter as the Fuels from Sunlight Energy Innovation Hub. Congressional appropriations allowing, always have to have a little fine print, this is $122 million over 5 years. It was $22 million in the first year. It was supposed to be $25 million in the second year. But as you know, we had a little deficit budget problem in our country that we weren't under a continuing resolution. So we were awarded 22 in our second year, and we're now slated to get the full 25 in the third year. That can change, but at least there is support from the House and the Senate in this challenging budget environment to do this. The other thing that's good about it, from my viewpoint, is it's completely, as it ought to be, nonpartisan. No matter whether you're for energy security or environmental security or reducing our dependence on foreign oil or all of the above, nobody could argue against finding a clean, cheap way to make transportation fuel. Because after all, although we can electrify our cars, I've never yet seen a good plug-in hybrid airplane. And 40% of global transportation fuel is in stuff that cannot be electrified, is in ships, heavy-duty trucks, and aircraft. And there arguably isn't enough biofuels if we use them exhaustively to even meet that demand. So we've got to find a way to make carbon-neutral liquid fuel to reduce our dependence on foreign oil and to do it economically and environmentally secure. That's the party line. So what's JCAP? Who's we? We is Caltech and our major partner is Lawrence Berkeley National Labs, former home of our Secretary of Energy, Steve Chu. And it's a public-private partnership in that sense. We take a leading research university and a leading national laboratory, and we combine hopefully the best of both of what they have to offer in skills, talents, and operation into what is essentially a startup company approach. We have a highly focused research agenda. I had a lot of friends that many of them are less of my friends now in solar around the country, even at my own and local universities, that we said, no, you can't be part of our proposing team, because although you're doing really interesting things, we felt strongly, our leadership team, that we had to focus, that we were not going to be another funding agency, and that we would not win if we were just a channel for Washington instead of funding a portfolio of solar research to fund a portfolio of solar research. That wasn't our job. Our job was to actually take a few cards and go all in and see if we can bring them from inception in the lab into reality in 5 years, where it would have taken 30 to do that under business as usual. Okay, so that was our challenge. We have 2 divisions. The secretary wanted things under one roof. Well, we stretched the roof a little bit, kind of as big as Highway 5, but other than that, it's one roof. One is to dramatically accelerate the rate of discovery, and I'll tell you how we're planning on doing that. And the other is on the science involving scaling things up at unprecedented speed. There are actually 7 now, not 8 partners. Our main partner is Lawrence Berkeley National Labs, where there is being built another JCAP site, bigger than the Jorgensen site that we have here. We have a small outpost at the Stanford, at SLAC, for the reason being that we wanted one building, only one, to get everybody under one site, but then it would have had to be in Fresno, and nobody wanted to live there. And so we settled on 2, one in the Bay Area at Berkeley and the other at Caltech, and we wanted to move our Stanford colleagues there, but we couldn't figure out a way to move the synchrotron. So we left it at SLAC, and we said, we'll own a beamline there, and we can do work there for that purpose, but everything else has to be in one of those 2 buildings. So it is. So our partners at Santa Barbara, Irvine, and San Diego, 2 of them, the UCSD, although we have some subcontracts to scientists that are professors there with their research groups, they don't do any work there. We pay for their students and postdocs and their salary only when they come and work in our building, because we value so much the value added of interaction, of getting everybody in the same place, all working on the same goal, that if you're not working in our building, you don't get paid. We're doing translational research all at once, not waiting for one, because if one takes 5 years and the next take 5 years and the next take 5 years, it's 80 years, and none of us will see the end, and I'll certainly be somewhere else than a professor teaching Chem 1. So we're doing them all at once. We're considering scalable and sustainable manufacturing the whole time, and we're trying to do things that only could be done by getting all of these people together in the same place at the same time. When I first joined the Department of Energy's research program, I was fortunate enough to do that in 1982 when I was an assistant professor at Stanford, and I moved here in '88. I went to my first DOE meeting, and the legendary Melvin Calvin, I remember still to this day, who was a giant even then at these meetings, stood up and said, and I was impressed, I was 26, it was my first grant. We had to go to these meetings to meet with all the other grantees, and he stood up and said, we better build an artificial photosynthetic system so we figure out what works and what doesn't. Well, in 2010, nobody had done that. So we went, of course, what happened in part was the price of oil went down to $8 a barrel. If you remember, President Reagan's first act was to rip the solar panels off of the roofs of the White House. Nobody cared very much about energy at the time. We lost 2 decades, 2 very, very precious decades worth of building an R&D base to help us solve these problems. So we're playing catch up fast. But, you know, on my watch, this is not going to happen. We are not going to go another 2 decades and not actually build something, because you can't know what works and what doesn't work, and you can't solve problems that are problems and not problems that aren't unless you face the real world, as all good engineers know, and build something and then figure out what the sensitivities are and how to make things better and how to not work on the stuff that already works well enough. After 30 years in research labs of artificial photosynthesis, we can get 2 out of 3. You want it to be robust, you want it to be efficient, and you want it to be cheap. And I can give you any 2. If you want it robust and cheap, it isn't efficient. You want it robust and efficient, it isn't cheap. You want it efficient and cheap, it doesn't last. So our job in JCAP is to go for the trifecta. We want all 3 at once. Now we know the blueprint. We know the Calvin blueprint. He figured out the Calvin cycle. We know how photosynthesis works, 2 photosystems. And the reason 2 photosystems is so important is because, unlike a solar cell, when you can trade current for voltage, if you buy a silicon solar panel, like the ones on the rooftop of the parking lot, they give you half a volt. And they give you a lot of current 30 milliamps per centimeter squared. If you buy a gallium arsenide solar cell, it gives you more voltage but less current. You can trade voltage for current. You can get half a volt, get 1 volt, do anything you want like that. But if we don't get 1.23 volts or more, we get 0. Because the first law of thermodynamics rules can't be repealed. And it says that to split water into hydrogen and oxygen, or to reduce carbon dioxide into methanol or gasoline or sugars and make oxygen, takes 1.23 volts or so. And so if you get 1.22, you get nothing. So we have a fundamental constraint that the solar industry does not have. We have to get the voltage needed to drive chemical reactions. Now, if you want to do that with one material, with one band gap, then what we've learned from the last 30 years is you can do that, but the band gap gets so high that you don't absorb much sunlight in materials that will last. In fact, the materials that last the longest time are the pigments in sunscreen. So if you want to, you can make these things that work all the time out of strontium titanate or zinc oxide or titanium dioxide, but they work much better for NASA on the moon than they do through Earth's atmosphere, which filters all that UV. Now, by the time you want to get the band gap down to where you can actually use it, you don't get enough voltage. And so you have to string together 2 photosystems, like stringing together 2 batteries in series in your flashlights, to get enough voltage and give up the current. You're getting half the current, but twice the voltage. That's exactly what photosynthesis does and why it does that. That's why plants are green, because they're absorbing red. They absorb 670 nanometers from chlorophyll. It looks green to us. They're absorbing red. And there's not enough voltage in one chlorophyll excited state to make fuel, so it strings together 2 of them. And it does 2 other important things. The first thing it does is that because we need it to be robust and we need 2 different chemical reactions, one to oxidize something like water, the other to reduce something like CO2, oxidation and reduction don't mix in the same place at the same time. That's what Timothy McVeigh used to make a bomb. Ammonium nitrate is an oxidant and a reductant in the same place at the same time. They react with each other thermodynamically. And the catalysts are unstable if they're in the same place at the same time. And so the oxygen-evolving complex, the manganese, is reductively unstable, but it never sees a reducing environment. It's inside a membrane where it only sees an oxidizing environment. The reduced proteins, the nitrogenases, the hydrogenases, the rubisco, the most abundant enzyme on Earth that fixes CO2 into reduced fuels, they're oxidatively unstable, but they never see an oxidizing environment. Nature compartmentalizes its reactions by ensuring that the oxidation never sees the reduction across a membrane that also separates the products so that they don't back react or go kaboom. Now, to do that, it also has to do one more important thing. It has to pass protons. Because if electrons are going to go across the membrane, then protons had better move too, or you'll charge it up and then you'll be making a capacitor and it will just eventually stop when the capacitive voltage equals the voltage you got from the sun. So you have to neutralize that charge to keep everything electroneutral, and that's what nature builds into the proton pumping in cytochrome C and P450 and so on. Right? So the functions of a membrane, of 2 photosystems, and of separating your reactants and products are the blueprint that tell us, like a bird, how to build an airplane. Now we actually, let me keep going. Okay. So we have short-term research. In 5 years, we think we can build the pieces and put them together into systems the size of this laptop that are going to be devices that I'm going to be able to show you and the president and anybody else that wants to know what Caltech did and led the way in order to directly, with no wires and no bugs, make fuel from sunlight. So we're going to do that, guaranteed. But our first product's never our last product, and the first iPhone's not the 5th iPhone. We always can make them faster, better, cheaper. We got to get off the ground and fly. We're going to do that, but we know that it's not going to be the end. We really want to get better components, better pieces, and advance the engineering by the underlying advances in science. And on top of that, we want optionality. We also know that the first and easiest, even though they're difficult, chemical processes will be to reduce water to hydrogen. Now, actually, we don't view hydrogen as the fuel we would use, because in fact, we already have chemical processes that can take hydrogen and CO2 and make methanol. And from the methanol, you can make diesel fuel or gasoline. And the energy content is about the same of all of them. So the key isn't to get hung up on which fuel we make, because we in chemical refineries can turn one fuel into another. That's what refineries do every minute, every day of the year. It's just to make any fuel, and we can convert one to another. So if we need to fly our planes, we're not going to fly them on hydrogen. We're going to take that hydrogen and make it into methanol and make it into dimethyl ether, a nearly perfect diesel fuel, or make the methanol into something else. Or we're going to take the hydrogen with CO2 and do what's called the reverse water-gas shift reaction, and then the Fischer-Tropsch process, the one that Germany ran its economy on in World War II by converting coal into liquid fuel, the one that South Africa uses today to run its economy because they're embargoed from oil, they make their own. So we already know how to convert one fuel into another. But that being said, it would be nice if we could make a liquid fuel instead of a gaseous fuel. And so we would like to directly, like a plant, reduce carbon dioxide from the air and make a liquid drop-in fuel. And we know that won't come first, but we're keeping our options open and our system having options so we can plug and play as we evolve that feature into our next iPhone. Right? So that's the strategy. So what do we have to do? Well, we have to have Earth-abundant light absorbers and photocatalysts. If they're not Earth-abundant, it'll be a scientific curiosity. So we have organized a team of people around discovering, developing Earth-abundant light absorbers and photocatalysts. And when they do this discovery, we will do it in revolutionary ways. Right now, it takes 5 years, a graduate student lifetime, for someone to take a material from the time they first make it to figure out whether it's worth pursuing. Because they have to purify it, they have to grow a crystal of it, they have to learn how to dope it, they have to make junctions to it, they have to measure its properties, they have to hook up wires to it and then measure its current voltage curves and then publish a paper with its diode performance. And they graduate. We don't have 5 years to do that for every new material that's out there because we'll never succeed. So we are using modern robotics to, instead of discovering one catalyst every 5 years, we're going to make and quantify the activity of both electrocatalysts and photocatalysts at the rate of 1 million every day. That's what only a hub can do. So I'll show you how we're going to think about doing that. But it really doesn't matter if we actually meet our goal, which we think we can, of 1 million a day or of 300,000 a day. What matters is what used to take 5 years is going to be done in 5 milliseconds. Okay? And we're going to have the world's largest database. We're going to make more catalysts in 1 day than have been made in human history. And we're going to expose the database of every catalyst composition we make and every reactivity as a bunch of numbers. And I'm happy to offer a prize to the person that can take the database and figure out how to tell us what to do next. It's what Netflix did, if you saw them, the contest, right? Good. Okay. So that's one thing we're going to do. Another thing is we need those catalysts because we've got to couple those electrons in the make and break chemical bonds. We have to replace platinum and RuO2 with Earth-abundant systems. So we have teams to work on that. And those teams compete because there are synthetic approaches like my colleague Jonas Peters here leads that make beautiful complexes that can be dissolved and studied by their mechanism. And there are other teams that make heterogeneous catalysts, supported ones like in the tailpipe catalytic converters. And those two communities don't use the same tools and generally don't talk to each other. And I said, as director, it's fine if you don't talk to each other, but the one that makes the catalyst that wins shuts the other one down. Okay, so when we get the catalyst, I don't care which one it is, you're both out of business. What else am I going to do? We have a team built around the membranes to hold them together. We have to have those membranes, and they have to be cheap, and they have to meet our properties that they can be rolled out like bubble wrap, and that they'll pass protons, but also connect electrically the top and the bottom, and not absorb any light. We have to have the potato head team. They have to put them all together, and it has to work. We have to have these emergent phenomena. We're using micro rods and nano rods developed by Harry Atwater here and myself, our teams of graduate students and postdocs, for reasons that I may or may not get to, but are good technical reasons. But it's one thing to have one nanorod or microrod oriented toward the sun. It's another thing to have square acres of them all oriented toward the sun. And so we need to learn how to get them pointing all together in cheap methods, but they don't have to all point exactly up and down. They could be like blades of grass on your lawn when most of them do. So actually, we've just developed methods when those rods are magnetically aligned. And I have a little present from one of my graduate students. When I was 4, I had probably you had it too, the little Willy Willy thing with iron filings, and you moved the magnet around and made his beard change into a mustache. Same idea. We magnetically align these little micro rods and then put them up and put them into a gel and freeze them, and then they all turn toward the sun and stay that way. So we develop methods like this. And then we have to scale up from the mesoscale to the macro scale. What do I mean by that? If we make something that's pretty small and it succeeds, it makes hydrogen and oxygen or CO2 and oxygen, we'll declare victory until we make our first tiny little bit of actual product. It would work great in a journal, just that after we get those first bubbles, those bubbles will block and refract the light and will prevent new reactant from getting to that 3-phase boundary or will clog our plumbing. And so we've recruited mechanical engineers and chemical engineers to understand. We have a bubble team because we had better learn how to nucleate, grow, direct, and avoid bubbles and flows and plugs in our system from the first day, because otherwise everything that's done here will have a bottleneck that would be impenetrable because it would be knocked out here. So we have a bubble team. And then we're building real prototypes. Those prototypes are going to be things that can be credibly manufactured at a credible cost out of materials that we know do not yet exist. So we have dummy parts. We have things that will work in the ultraviolet, that we can adjust the light intensity to get it just as if it were working in the visible region with the same flows and fluxes, so we can prove out how it works. And then, as the teams down here develop new pieces, we slide in the new, faster, better, cheaper versions of these prototypes. So every year, you can come back to me and say, what'd you do? And I'll say, we made this one 20% better, 40% cheaper, and 20% more efficient. We made this one differently, because this one is different than this one. It's a different design, and the research will go in fits and starts, and maybe this one needs the hydrogen catalyst, and this one needs the oxygen catalyst, so you enter several horses in the race and bet on them all. Don't just bet on the one that's ahead today, because it could end up not winning in the end. So we'll keep 4 or 5 parallel threads. And then we have people dealing with sustainable and scalable manufacturing, because after all, if the embedded energy involved in making this stuff is more than we're going to get out of it for the next 20 years, it doesn't do anybody any good. And so we have to look at that from the beginning also. So that's JCAP. We're under one roof, big roof, 2 buildings, one Jorgensen here at Caltech, the other a $53 million building, beautiful building with a view of the bay on the Lawrence Berkeley Lab campus is going up. I was just there this morning, actually, leading a meeting of all of the Energy Frontier Research Centers, 20 of them with our hub yesterday and today. So we're going back and forth a lot, and we use video conferencing also. And I am the director. We have a great support staff. Assistant director, an associate director. Xenia has a nearly unpronounceable name, so she goes by X. X marks the spot. X is great. And we recruited her from JPL, where she learned how to manage programs of science impeccably. And so we took some of their best and then took it into campus. We have projects that are roughly color coding, equally divided in some cases. In some cases, they're more in the south than in the north, because our clusters of instrumentation are going to support a bigger effort logically in one site than the other. For instance, the robots that make these compounds, they're all going to be here. It doesn't make sense to divide that task up. We can send the good ones to be worked on at all places, but that's all here, our high throughput experimentation. And the beamlines are all at LBL and at Stanford, so they have all that. They have better expertise in some of the scale-up, so they have that. We have better expertise in other things. The other thing that we do is we do not fund, ooh, this was a great thing, we don't fund professors. They don't get money. Project leads get money, and the project leads can be professors, but they wear JCAP hats, and their job is to get their job done. They can staff it with graduate students and postdocs, and they can hire staff, but they have missions and jobs, and if they succeed, you know how they're rewarded? We cut their funding. After all, if they've succeeded, we don't need to give them any more money. They should be helping us in something else. It has taken a lot of buy-in to get all of us, including me, faculty members, trained that success is rewarded by more funding, to actually sign on the dotted line to the enterprise that puts solving the problem higher than getting more money to solve the problem. Right? So it's an experiment in innovation. Right? The other experiment is that every project has a lead and a co-lead where either one or the other is from the north or the south. So we have National Lab and UC Berkeley representatives working on the same project as co-leads with Caltech or UC San Diego, Irvine, or Santa Barbara representatives. And the projects that are done in the south or north are linked by routine video conferencing that actually Caltech wrote the video code for. It's used by high-energy physicists around the world. 200 scientists can get together at any time and see each other in windows and share PowerPoints and do all sorts of things. It's kind of like Skype to the nth power, and it's great. So we use it all the time. Okay, let me get you a little bit of our science. This is what one of our structures looks like on PowerPoint. After all, we knew nature had a membrane, so we want to build a membrane. Now, fuel cell people have used membranes called Nafion that satisfy those needs, so we can just steal that right from them. But they don't have the light absorbers. We could use a planar light absorber, like something that would be used in a photovoltaic cell. But in fact, the reason that we don't want to do that is twofold. We have to move protons up and down, so we need holes in that piece of material. Otherwise, the protons can't move, and we can't neutralize that pH gradient. But the other problem is that it's constraining to make a planar sample. Because if you have a planar sample, then you need a certain thickness of silicon to absorb light. And that thickness is 200 microns. That's why all solar panels made out of silicon are 200 microns thick. Any less, you waste photons. Any more, you waste silicon. That's a law of physics. But it also dictates why they cost so much money. Because the photoexcited carriers deep in the silicon have to last long enough to make it the 200 microns back up to the top to get to the junction to get separated to make electricity in the wire. And to purify the material sufficiently that the carriers make it all the way back up is why that piece of silicon is the purest thing that any human will ever touch. It's purer than a part per billion, purer than the purest diamond. I mean, silicon is diamonds are forever kind of thing. Because you have to make it that pure or these carriers just make heat instead of making electricity. So it would be really great if we didn't have to purify it that much, if we didn't have to make the carriers last all the way back up to the top as they were created all the way back in the bottom. So that says what you should do is not make them go all the way back up the top. You should just make them go sideways. So that if you can absorb light over a long distance, but make them go sideways to a short distance, you can use really cheap stuff because they only have to last this long instead of lasting that long. This was an idea 5 years ago, to make nano or micro rods of silicon, for instance, that could efficiently capture and convert sunlight and be exploited because, of course, fuel is the perfect way to conformally make a contact to these radial junctions because the liquid will fill up conformally all the sidewalls of this structure. So Harry Atwater's group and my group worked on this very hard in collaboration. We formed a team of people to do this, and we grew rods like this of silicon in membranes like this that could pass protons that in fact now have the world record for hydrogen production directly from sunlight in both efficiency and in cost effectiveness. We also showed that you could make electrical contact to these things conformally by filling them in with a different polymer and covering the top, and you could make flexible, bendable solar cells. The Moore Foundation at Caltech, as well as the National Science Foundation and the DOE paid for that. We just proudly closed on a venture capital funded startup company to make flexible, processable, silicon-based solar panels that can be rolled out on your roof with 2% of the silicon that you would use, cheap silicon compared to the solar rooftop silicon. And that's going commercial as of this afternoon, actually, is our first employee paying. So that's a Caltech spinoff. But although we hope that succeeds and makes lots of electricity, we want to make fuel ultimately. So we want to use those things to be our rods to make fuel, because that's the strategy nature tells us. Have the rods, have an absorber, have a membrane. But you can see that's only halfway to where we need to be, because this is the bottom half. It makes hydrogen. Now we need the top half to make oxygen. Silicon has this one little two problems. One, it only gives us half a volt. Top and bottom half a volt add up to 1. I already told you what happens when you get 1 volt. You get 0 current. All right? So we need another material that gives us more voltage. And silicon has another problem. It makes sand when it's in an oxidizing environment. And sand, SiO2, is a great electrical insulator. And that's really bad news, because we can't pass any charge through that if that's what we make. So we like it for the reductively stable part, because you can't reduce silicon anymore. It's already all reduced, and it's stable and can support catalysts that can make hydrogen. But we need another material with a bigger band gap that's oxidatively stable to make oxygen. And that's the other piece of the blueprint we get from nature. This is stable reductively but not oxidatively. This should be stable oxidatively but not reductively. Combine the two voltages together to get the one voltage big enough added in series to make the fuel, put them in a membrane to separate the products and pass the protons, and then roll it out on your roof. Well, it would all be great if we actually had that material, but nobody knows what that is. That's what we're going to try to figure out. Okay. So what do? One thing we do is we think we're smart enough to know where to start. So we know that there are catalysts like nickel molybdenum, molybdenum disulfide, that can reduce hydrogen, make hydrogen from water, that aren't as active as platinum, but that are pretty active, only if we expose the edge sites and not the planar sites. So we're building up surface science capability, electrochemistry, and because on these rod-like structures, we don't just have a plane. We've got a lot of internal area to support our little catalysts. And that means we can load it up with a lot of catalysts. And so if it turns over 100 times more slowly than platinum, but there's 100 times as much of it, it's just as good. So we have a strategy to replace these non-earth abundant metals with earth abundant ones that cost a lot less, so that we can scale them up. In fact, this diagram has now become a poster child for an entire solar fuels community of 300 research groups in many different countries, and it was drawn by one of my very artistically talented and Adobe Illustrator competent graduate students, Liz Santori. We joked that if she had a nickel for every time someone used this, she would be rich. She says she doesn't need the nickel, but her initials are somewhere in microfiche, somewhere on one of these diagrams. So she knows it's been watermarked. The other thing we're going to do is, because although we think we're smart, and we think we have theory that can help guide us, we know we're not that smart. And so we are going to use an inkjet printer to squirt out every combination of everything we can think of. Now, we use a custom inkjet printer. It costs $120,000. And so, for instance, there are only 18 or 20 elements we care about. We have a custom microfluidic mixer that has wells of inks that have every one of those 18 elements in it. And it's just we tell it to mix those things, just like mixing different colors. It squirts them through the nozzle onto a drop. We make those drops onto a pallet where every one of them is connected to a different electrode. We then address those electrodes in rows and columns with switches, the left row and the right column. And how do we do that? We just do exactly what's in my laptop and in every plasma TV. That's exactly how it works. All right, there's a row column addressing on a connector from your computer, and it has a pixel underneath every LCD pixel. There's 4 million pixels just in this display. There's more on my plasma TV. All you got to do is take apart this display, use the same backplane, use the same control electronics, and squirt with an inkjet printer on top of it everything you want to measure at every pixel, and then use the control electronics to switch them all, and read all those currents. And since the current is the chemical activity we want, we'll get a current for every different composition, and we can squirt out gradients, we can make arbitrary mixtures, and if we have all of the 18 different inks developed, then we'll be able to, on order, have every good idea pursued the next day. Okay? So when I said we will discover 1 million compounds a day, I think there's no question we will, because we've already shown all the steps in lab scaled up by 10 from a graduate student to a machine can get us that easily. Okay. Light absorber is the same thing. It's easy to figure out if you have the right band gap for a light absorber. Not only do you think you're smart and you make directed light absorbers, you can use the same inkjet printer or pulse vapor deposition or electrochemical detection pipeline technology. And it's really easy to tell when you've made a semiconductor with the right band gap. You just take a picture of it. If it looks yellow, you don't want it. If it looks green, you do, because absorbing in the red. If it looks black, it might be okay, and you can look through an infrared camera to see if it's too black and it's more like graphite or soot, or if it's more like silicon. So we can rapidly screen the band gaps. We can then turn this around to theorists and say, here's the biggest database in human history of light absorbers versus composition, since we know what every one we put in, and now go use that and actually predict where we should be looking next. And if you can't predict it, we'll do it faster than you can predict it, and we'll come back to you and you can catch up to us. Okay. We also have a benchmarking function. The benchmarking function we think is very important. We have 2 professional staff to be hired, one already hired, Charles McCrory, and his job is to be the underwriter laboratory of catalyst and photocatalyst benchmarking in the world. Because we hear a lot about people always naturally claiming, putting their 2 best feet forward. I have the best catalyst in the world. I have the best catalyst in the world. My catalyst is better than yours. But you know, at some point, somebody has to compare whose activity is better than whose under a standard condition if we're to make progress as a scientist in a community. And we have to see how they stack up. And so their job is to just measure on a fair footing, under conditions that are standardized, everybody's activities from around the world, and Caltech is going to be the central collection of all of this information that we'll post on our website and then publish in the scientific literature and update it. So we'll know what the score is all the time in the game and be able to use the best pieces from anywhere, not only internally, but in the scientific community. In addition, we have to put everything together. So we have these catalysts, we have these light absorbers, we have to learn where to put them. If we put them on the top, that might be good, except that maybe we want them further down where more light is absorbed. If they get too far down, they might form bubbles down at the bottom, and the bubbles will go through these materials and then block further access from the top. We have to learn where to put these things so they work together as opposed to just working independently. We have to learn the right shapes. Maybe we don't want rods. Maybe we want pyramids with little points on them. Maybe we want cones. Maybe we want aspen trees. Maybe we want pine trees. So we have people making different shapes of materials. Nature figured out how to optimally get light. You know, this audience will know. So if you look at a pine tree, its rotation is in a Fibonacci series from the main branch to the next branch and so on. And, you know, it's 1 over 1 plus 1, so it's 1 over 2, and then 1 over 1 over 2 plus 3, 2/5, and so on. And Da Vinci discovered this, and of course, if you figure out why that should be, it's because then it has optimal transmission and minimal shading of one branch relative to the next. Okay, so nature figured out how to optimally get light transmission from the top through the canopy down to the bottom. So what pine cones do, it's pine trees, Christmas trees, they all have this natural pattern. There must be feedback control to do that, because how would a branch know how to grow out relative to the other branches? It must start to grow and then stop if it's got too much shade, and then favor something else that grows more under more light conditions. That one takes over, that one stops. There must be some feedback. So we're trying to understand how to impose feedback control to get optimal shape of these things and optimal branching and still get ions coming in and out of these things. There's great science to do here, but you don't even think about doing it unless you have this application in mind. we have to put all these pieces together into this membrane. We think our membrane looks like a high-performance rain jacket, where in fact the top layer doesn't have like solar panels with protective glass, but is just watered like your lawn, because all you got to do is keep the stuff wet. And then you vent the oxygen through the top layer, just like your rain jacket breathes. And then the light absorber is in the middle, and then the bottom layer is where you wick out your product. That's all you should need. No bugs, no wires. You should be able to roll it out and collect your fuel. So that's what the key components are that we're trying to develop. That's the vision. But that means we better be making multifunctional membranes and understanding how to put them all together from the beginning. So we have a membrane team trying to do that. And then we have our bubble team, because if we do that, that bottom layer wicking, we need to understand the network of flows so bubbles don't cream us. And then we have the prototyping team. We have one of these rapid prototyping machines. We just got it 2 weeks ago. It's in the Department of Mechanical Engineering under their control, but at JCAP North at Berkeley. And it's a three-dimensional machine, rapid prototyping machine. We just made a wrench with threads and everything in half an hour, a three-dimensional object from a CAD diagram, and it's a plastic thing, and it's spit it out. And we can spit out any prototype we want with any set of compatible materials that can be clear, that can be colored, that can be bendable, they can be any shape bolted together or layered. And so we can turn around our designs very quickly to try to get these prototypes made and proofed out and working, so then we can slide in our real materials as they evolve. Okay. We have access to beamlines. We have unprecedented access to the world's brightest soft X-ray source, the advanced light source at Berkeley, and to the world's will-be brightest hard X-ray synchrotron source at the Stanford Synchrotron Radiation Laboratory. We got that as part of the deal to let them be our partners. They had to let us use their facilities. Strike a hard bargain, but, you know, it's part of the business. We're teaching some short courses. We're trying to get corporate partners because, after all, if the government's putting in $25 million a year into this effort, which it claims to be doing, and we claim to be doing something that will make a difference, then industry should be paying attention. And so we want people to help us from beginning to be bought into making basically an entirely new product. I mean, there is no product that makes fuel from the sun with no wires and no bugs today. And so it's an entirely new market, an entirely new product. It's the first iPhone. It's the first iPad. It's the i-something. iFuel, right? This is what Jorgensen's going to look like in April. It'll be entirely redone. Now you don't see the glass or anything. You can see right through it. You know, Jorgensen is a strange building because it has a central core, and there are just 4 structural posts internally, and the rest of it was all just there. It's not structural. So the easiest way to re-gut it and knock it down was to knock down all the walls. So you see it now. It looks like a house of cards if you go over there on the way to the aft tonight. You can walk by Jorgensen and see this little central thing and 4 posts, and you can see right through the rest of the building. So the Resnick Institute will be on the first floor, sharing some conference space and having its office headquarters there. And then all the rest of this building will be for JCAP South, where there will be, at steady state, about, we think, between 80 and 100 people. So it'll be a very healthy size project, especially for a campus the size of Caltech. And we'll have another 60 to 70 people at Berkeley under our budget, all working together as a team, all matrix through video, all the time trying to work on this problem. It's very, very exciting. They have a beautiful building going up with a beautiful view of the bay. It's a $54 million facility with skylighting, and we'll have a demo space on the roof for our devices and all of that good stuff. We have this little Evo video conferencing thing that we use. We're going to try to get telepresence in there because we have a fat pipe with high bandwidth at, right next to Jorgensen, so we can pull that pipe onto the fiber optic network, so we'll be able to see our colleagues in real time. It's an experiment in innovation as much as it is an experiment in science. People ask me what our product looks like. I've told you, it kind of looks like that. You know, it looks kind of like bubble wrap that you'll roll out, that you're just going to water as the fuel with the sun, and then out comes the stuff you really want in the end when we succeed. We have these 20 energy frontier research centers all around the country. I just had a meeting that we organized with them. That's where I came from this morning and yesterday at JCAP North. They all are providing inputs to JCAP because they are basic research centers that in part can help justify their output of science by providing things that are relevant and input to the hub. We can't do everything, and we depend on our colleagues working on these other projects that DOE is making an investment in, along with the National Science Foundation Center for Chemical Innovation, led here by Harry Gray. And we need all those inputs because if they develop the best catalyst, we want to use it. If they develop a membrane we need, if they develop some theory we need, we want to incorporate their advances into our hub so that we take the best from everywhere and then help it to get us forward. So JCAP is, I told you it was a bold experiment. It is still an experiment. The buildings are not yet built. We think a lot. We have $25 million of equipment being purchased between those two sites that is new equipment with new capability. We're trying to get it all stood up and running and operational. We also, of course, have temporary space, but we are trying to bring everybody together, not disperse it out into the departments, even on a small campus like Caltech. So no work will be done on JCAP in my labs, in Noyes, or in the Beckman Institute, or in Watson. Harry Atwater's people that are working in JCAP are going to be in Jorgensen. My people that are working in JCAP are going to be in Jorgensen. Harry Gray's people are going to be in Jorgensen. John's people, no matter where they are, no matter who they are, it doesn't matter if you're a mechanical engineer working on prototypes, or if you're a chemist working on catalysts, or if you're Jolie Kornfeld's people or someone working on membranes. If you work on this project, you work on this project with people who live, die, think, and breathe this project. It's a very interesting model. We'll see if it works. It's very exciting. We're also, of course, as you'll see, struggling to finish Jorgensen because it costs more than we thought. So if anybody has a good idea how to help raise a couple $1 million for it, let me know. We're still trying to do that. This is our all-hands meeting at Asilomar in April. This is 1/4 staff of JCAP, because that's what our budget was in our ramp-up phase. This gives you a perspective for what this effort means. Yes, we have JCAPs, right? You can have one, maybe. There's some humor here. The other interesting thing is that we're going to run out of consonants pretty soon, because after the United States, of course, announced that, and the Secretary of Energy said this is going to be our basic energy response to climate change and to energy security, is to challenge our scientists to do this in a big way, that it didn't take long, but we're JCAP, and there's already a KCAP. There's already a Korean Center for Artificial Photosynthesis. There's another JCAP. There's a Japanese Center for Artificial Photosynthesis. There's a BCAP, a Brazilian center. There's a Chinese center. There'll probably be a European center. And the two interesting things are they're all funded at higher levels than we are. And their express goal is to beat JCAP. That's what they say. And they all want to send people here to learn from us the blueprint on how to do this. So of course, science is international, and of course we want to collaborate. And of course, when I tell my contacts in Congress about this, and they say we're in a challenging budget, then the answer really is that you either cut the legs out from under us when we're leading the race, or you bet on America, right? So if they bet on America, if they think that what we do best, which is innovate, that what we do best is get our smart people working on important problems, and that that's the way to help move everybody forward, if they bet on us, then we'll deliver. That's what I tell them. So we'll see if we're right. So with that, thanks so much for listening, and I'm really happy to answer questions.
Were you able to break any new ground in the intellectual property issue?
Yes. I don't know about new ground. The question was, what do we do about intellectual property? This was actually a topic of discussion earlier today with these other 20 centers of what do we do. And so there are a few points. One is that we already do have in place an interinstitutional signed agreement with all the JCAP partners. And it's, as you would expect, not completely conventional. We had to break down some barriers there. And it is an all under one umbrella. So it doesn't matter if you're at Berkeley or if you're at Caltech or if you're on the phone from UC San Diego. If you're in JCAP, you're in JCAP. And everybody has signed an interinstitutional agreement to share the intellectual property. There's a formula about how they divide it up and things, but there's one point of contact for licensing for all of JCAP. There's one entity that collects all the intellectual property. And therefore, for me as a scientist, I don't have to sign a visiting scientist agreement when I hopped on the plane today and happened to land at Berkeley. They didn't own me this morning, and now I'm back here and Caltech owns me. JCAP owns me, right? When I'm a JCAP person, when I'm doing my NSF research, I'm Caltech. But when I'm JCAP, JCAP owns me, right? And they own my intellectual property, just like they own Peidong Yang, my colleague at Berkeley, who runs the Berkeley site. And there's a predetermined formula on how to handle this single one-stop shopping, and it's all supposedly worked out. Now, of course, we don't have any patents yet really to worry about licensing, but we have some filed, and we hope that this works. The other thing was that although there will be lots, we believe, of very valuable intellectual property, we think even the robots that discover catalysts and the catalyst will be valuable because we're going to have the world's biggest catalyst library. And the reverse reaction for the one that we care about to make fuel is to consume fuel. We're not going to look at them as fuel cell catalysts, but someone, I'm sure, will want that library to look at them for those catalysts, or to look at them for other reactions, or to use our methods to do things to look for other reactions, or to take our new materials that we want to make fuel out of and use for solar electricity, or on and on and on. So there'll be lots of intellectual property that come out of this that we're very excited about developing. At the same time, and I told them this morning, everybody this, that my philosophy on this is this problem is too important to let intellectual property get in the way. Okay? So we will use best efforts to not let it be a barrier reciprocally. I mean, we're not going to block other people on purpose, and we don't want them to block us in the sense that it's not a one discovery. This is like building an airplane. If you have an engine, you don't have an airplane. If you have a wing, you don't have an airplane. If you have a fuselage, you don't have an airplane. You have to put the pieces together. They all have to work. They all have to work at once, and the plane has to fly. So if your catalyst is patented, that's fine. But if it doesn't work where my catalyst works at the same pH, where my light absorber works, where my membrane works, nobody has anything. So we have to all work together to improve those things, to get them into the system to all work at once. And the only way we can do that is if you let me see what you have, and I'll let you see what we have, and then we can all be better off all collectively if we cooperate and get them to work together. Otherwise, separately, we have nothing anyway. Okay.
So who owns the end product?
Who owns the end product?
When you get all this together, if I'm a manufacturer and I come to you and I want to build a plant that uses this.
Right now, so of course legally, the inventing entity And if there's lots of joint inventions, they would be jointly owned. But then there's a question of to whom do you come to get the license to the patent? And the agreement is that you come to the lead institution to get the license to all JCAP patents. And the lead institution for JCAP is Caltech. That doesn't mean the royalties wouldn't be split amongst inventors and inventing institutions. But if you're an entity that wants to commercialize this, then your one-stop shop that is the licensing point of contact is the Caltech Office of Technology Transfer.
Let's suppose we have 5 trees in the San Gabriel Mountains, and they decide it's time to make a little forest and make 15 more trees. They don't grow the trees in China and ship them here using photosynthesis products. They've learned something about the way this fuel is used relative to the task at hand. I think that might be a concern that even you, with such a fine project, need to think about. In other words, they transfer information about how to make themselves rather than the actual product.
Yeah, this is very interesting. But we have a tension here between, which is a tension that comes out even more in a project like JCAP than it might in normal university research of at what point do we decide we have a job to do and we'd better narrow down our focus versus keeping alive all sorts of other interesting options that may prove to be the dark horse and be the really important thing, but we've shut them down prematurely because other things were more promising for the shorter term portfolio. And I, as JCAP director, have to make those calls on which things at any given point in time are risky enough but rewarding enough to still be doing in JCAP as opposed to having done somewhere else and then waiting for JCAP to pick them when they're ripe, as opposed to we got to do it internally. And that would be one of those things. Do I need something self-adapting and smart in order to get done what I need to get done? And if we worry about does this country ever have manufacturing capability, that's a bigger problem than my pay grade. Or do we worry about that from the beginning and try to end run it? Right? So that's a tough call. A lot of tough calls here. Of course, we just want to get something on the books working right now, right? So we can learn from it and make mistakes and then improve later on. So our philosophy is don't reach. You got to walk before you can run, and we're not going to swing for the fences when a bunch of singles are okay. We got a lot of work to do, and we've got a lot of different things. And at some level, you could say this sounds nearly impossible. That's exactly what Edmund Land said. If you read it, you should work on as a scientist. Something that's nearly but not impossible, but that is really worth compellingly doing. All right?
Is this on? 2 items. I'm not quite sure from your drawings whether these are rods or tubes.
Okay. So actually, we don't really care if they're rods or tubes, but the ones we've made are rods. They're not hollow. Although a colleague of ours, Craig Grimes at Penn State, has made tube versions of many of these things. And tubes are good and bad. They're good in that you get access inside as well as outside. They're bad in that you don't get light absorption from the solid object. So you only get it from the volume that can absorb, which is the soda straw, instead of all the stuff plugging up the soda straw. We don't know whether we want them rods or tubes or cones or inverted funnel cones or branches. So in fact, I have a graduate student getting a PhD thesis on shape control of these materials and which shapes are the correct ones that optimize these things, for instance.
The other was, my distant recollection was that chlorophyll absorbs peaks in red and blue.
Right.
And that there's alpha and beta, and one process is in the light and the other does not require light. Does this apply anything to similar to what you're doing?
Well, actually, yeah, there's a peak, right, that, in chlorophyll, but even though there's a peak and a dip in the optical thickness that you see in a canopy, essentially all the light's absorbed from 670 to the blue. So it's not like if you looked through a plant, you would be at 500 and it would be transmitted with a blue-green laser, for instance, right through the canopy. It's still absorbing essentially all of it from 670 higher in energy. Now the question is, there are light reactions and dark reactions. Respiration is the dark reaction, right, that undoes essentially photosynthesis. And we don't want that, right? We want to drive the photosynthesis. We don't want our things to do the reverse. We think that's a back reaction that we kind of call undesirable in our case. It's part of the reason that they're only 1% efficient, and we want to drive them all one way. There's one over here. I'm going to dinner tonight, so I have plenty of time. I can stay.
This whole project reminds me a bit of the Manhattan Project. Is that a valid comparison, and do you draw any lessons from that?
Well, actually, so I'm a student of innovation. I'm proud to say that. And when putting this together, I studied, and I actually have some colleagues as part of an advisory group that I do that were in the Manhattan Project, and asked them what it was like. And of course, we had Feynman here, and there were several others, and also Bell Labs in its heyday, right? And so those were two kind of hallmark institutions. Now, they both had two features that we don't have in different ways. One is, scientists moved, to Los Alamos, right? We were at major war, and there was a sense of incredible urgency then, and so people were willing to leave their universities and go out to the middle of the nowhere desert, right, to work together kind of all the time. So capturing some of that sense of urgency and making this not another project business as usual is something that, I think is my job as director, because, that's what we want them to have, right? We want our graduate students and postdocs to have that. And so that part we tried to capture. The thing we haven't been able to do is, we spent 10% of GDP on the Manhattan Project or something. So, and Bell Labs had essentially unlimited funding because, they were basically a tax mandated. It was a government-funded monopoly. The phone company, everybody had a telephone, a landline. Everybody paid a fraction of their monthly bill that went into Bell Labs. So they could put many teams of people competitively on the same problem. And then whoever won got a pay raise, which is what they did, actually. Okay? So we studied that model and decided, because everybody around the country wouldn't move, and because we didn't have unlimited funding, and actually, if you ask me, like the CEO of a company, I have a budget, and I have a technology development stream, and I know where the risks are, and I know where the speed bumps are going to be and the gaps are, that probably really where my marginal value for our dollar would be, it's kind of like probably at $40 million a year. That's what we really kind of would be able to use. So even $25 million to do all this stuff in this time a year, we could use another 10 productively, really productively, to poke some holes, and we're delaying some things that we should be doing now optimally, but we're not. And some of the people are always, to get good people, more expensive than you budget. So we don't have unlimited money, and we don't have everybody in the country all willing to come to Jorgensen. And for those two reasons, we structured things somewhat differently than that. So it's more like Manhattan, Kansas, instead of...
Okay, this will be our last question.
So we're getting sunlight, right? And you're going to make some hydrogen, which is what you're after, and then you're going to do whatever you're going to do with the hydrogen.
Yeah.
Any thought about the oxygen?
Oh, we don't want that.
What are you going to do with it?
We're going to let it go back into the air.
Okay.
There's a good reason for that. Okay, so why did I flip it? Right now, when you electrolyze water, you do it to make the valuable product, which is the oxygen that you can use industrially, purified. And there's really no market, even though we talk about it a lot, for the hydrogen made by electrolysis, so people vent that. In fact, we make a lot of hydrogen right now, we collectively, that we throw away because I think 4% of the nation's electricity is used in electrolysis of saltwater brine to make the valuable product chlorine, venting away the hydrogen. The chlorine makes bleach, We use the bleach all over the place, and we use it for petrochemicals to make the chlorine. And we throw away the hydrogen because people want to pay for the bleach as the product. Now, if you want to make a fuel at large scale, you have to carry the reduced form and get the oxidized form from the air. Okay? So you've got to get the oxygen from the air, otherwise you're a battery, because you're carrying both your reactants and then your products. So if you're going to make a fuel, it doesn't matter what reduced fuel you have at the first order. It could be hydrogen, it could be methanol, it could be butanol, it could be ethanol. Ethanol only has 2/3 the energy density of gasoline, so you'll never fly airplanes on it. So we want a more energy-dense fuel ultimately than that. But you've got to make the oxygen so that you can vent it for free, so you can pick it up for free out of the air somewhere else when you want to close the cycle. Okay? So we don't really want it because we don't want to carry it around, but we want to essentially get it for free, which is what all of our cars do. They get the oxygen to combust the gasoline for free from the air, and then they vent the CO2 out the other side. The other interesting thing people sometimes ask me is, aren't you going to use ammonia as a fuel? Why don't you think about that? I'm perfectly happy to use ammonia as a fuel, because how do you make the ammonia? You have to make the ammonia from something, and the way you make it is you make it from hydrogen and nitrogen. So if I have the hydrogen, I have ammonia, if that's what you want to use. If I have the hydrogen, I have the methanol, if that's what you want to use. If I have the hydrogen, I have the diesel fuel, if that's what you want to use. So that's what I said. I'm completely actually end fuel agnostic, but it's getting the energy to make the fuel into some kind of bonds to then make what chemical engineers know how to do already, one fuel into another. That's not the hard part here, and it's not the valuable part on the energy scale. The other thing you can think about is, so in my view, why don't we want to use ammonia at large scale, and what are the choices? Well, the problem with ammonia is we have people that study biogeochemical cycles. We know there are 2 nitrogen cycles, right? There's the reduced one, nitrogen N2 to ammonia, and the oxidized one, nitrogen and nitrates. And you don't want to slip into that oxidized cycle if you want to run a nitrogen to ammonia and back reduced cycle. And the same thing with phosphorus. You have the reduced cycle, and then you have the oxidizing phosphate cycle. And you don't want to slip into the fertilizer cycle if you want to use it as a fuel, like you don't want to slip into the NOx cycle if you want to use ammonia to nitrogen as the fuel. And so even a small fraction of slip will turn out to be very problematic or toxic or polluting, whereas you don't have that with water and hydrogen or with carbon dioxide to methanol or carbon fuels and back again. You don't have that possibility of slipping into another biogeochemical cycle. And that's why I favor strongly a reduced fuel that is either in the hydrogen-water cycle, just hydrogen, and or using it in the water, in the CO2 reduced carbon cycle. Good. We're done.